Hi class, today we're going to talk about motion graphs so that we can solve this type of problem. This type of problem, for example, asks which pair of graphs represent the same motion of an object. And so before we attempt to solve this problem, let's look at motion graphs. Okay, so we're going to talk about two things. We're going to be talking about graphs, and I also want to introduce, which I think we've already mentioned, acceleration. I want to talk a little bit about acceleration. All right, so once again, there's two situations we have. We're talking about straight line motion, and we've got a situation where we have constant velocity. So we're driving in a car and we're going at a steady speed down the road, or we have a steadily changing velocity. So we're driving our car, but we're getting gradually faster and faster and faster, or we could be getting gradually slower and slower and slower. Okay? Now, acceleration is simply a measure of how much the velocity changes per unit of time. So let's say per second. So in this case, if I look at my speed at each second, so I would say my speed, let's say this is 3 meters per second, 3 meters per second, and it's 3 meters per second now. It's 3 meters per second a little bit later. It's 3 meters per second a little bit later. It's 3 meters per second a little bit later. It's 3 meters per second a little bit later. Okay, so it is not changing its speed. Okay, so it's a steady speed. So we would say the amount of velocity that's changing each second is 0. So we would say the acceleration, which is our change in velocity over time. Well, each second, let's say 1 second of time, we had 0 change in velocity. Our speed did not change at all. And so we would say our acceleration is 0. Okay? And the units of acceleration are just how much the speed changed, meters per second, each second. So how much did my speed change in meters per second each second? And in this case, when we're moving at a constant velocity, our acceleration is going to be 0. When we're moving at a steadily changing velocity, let's say we're getting faster and faster and faster, we start out at, let's say, 3 meters per second. And let's say a second later, we're going 5 meters per second. Let's say at 1 second of time, we were going now 5 meters per second. And at 2 seconds of time, we're now going at 7 meters per second, right? So we're getting faster and faster and faster with time. In this case, we would say our acceleration, which is our change in velocity versus time. We would say, well, let's just focus on this first second. Our change in velocity was plus 2 meters per second. We went from 3 meters per second to 5 meters per second over time, which was 1 second. So in this case, we would say our acceleration was 2 meters per second. Okay? So that's all acceleration is. It's just really the rate of change of speed or the rate of change of velocity. So if we're getting faster at a steady pace or we're getting slower at a steady pace, we're going to have a constant acceleration. And that's basically what we're going to be measuring, or that's basically what we're going to be recording. That acceleration is how quickly the speed is changing, that rate of change of speed each second. Okay. All right, but today we want to focus not only on acceleration, we also want to focus on our two situations here, and we want to focus on graph shapes. And so the first thing we need to talk about is what exactly are we going to be graphing? And so let's look down here. All right, so there's going to be 3 graphs for each of these two motions, right? We have our constant velocity, which we've been talking about, and we've got our steadily changing velocity, which we've been talking about. But we want to look at that motion, and we want to look at it not only to monitor the speed, but we also want to monitor the location, displacement, and we also want to look at how the how acceleration versus time changes. All right, so let's do an example. Let's say we're here at location 0. We're just picking some location to be 0. And let's say we're moving along at a constant velocity of 2 meters per second in the positive direction. So this is positive 2 meters per second. So what that means is 1 second later, we'll be here at positive 2 meters. We'll be here at 1 second. And then another 1 second later, we'd be at positive 4 meters. This would be after another second. We'd be here at 2 seconds of time, and so on. Every second, since our speed is 2 meters per second, every second we cover an additional 2 meters of distance or displacement. Okay? And when we're traveling in a straight line and we're not changing direction, distance and displacement are really interchangeable. So we could call it distance, we can call it displacement, sort of, because if we're moving in the same direction, the distance is going to be equal to the displacement. The displacement simply includes a direction with it. Okay, but anyway, so if we're moving at 2 meters every second, after 1 second we've gone 2 meters, after 2 seconds we've gone 4 meters, after 3 seconds we've gone 6 meters. Okay, that makes sense. So we would say in this particular example, our displacement started out at 0, and then 1 second, 2 seconds, 3 seconds, and we're going to be at 2 meters, 4 meters, 6 meters. Okay, so it's going to be linear. Okay, so if we're moving at a constant speed, our displacement is going to be linear. Okay, and what is our acceleration? How's our acceleration going to be changing with time? Well, if we're not speeding up or slowing down, as we said before, our acceleration is simply 0 meters per second each second of speed change. And since we have the whole time, we're moving at a constant speed, our acceleration the whole time was 0. Okay, so whenever we're traveling at a constant speed, constant velocity in a straight line direction, our velocity versus time will be steady by definition, right? We're moving at a constant speed. Our acceleration will be 0 because the amount that our speed is changing will be 0. And our displacement or our location will be linear. Okay, so we want to make an association between these three graphs. Whenever we're moving at a constant velocity, we're going to have a 0 acceleration graph, and we're going to have a linear displacement graph. All right, what's our other motion? Our other motion is a steadily changing velocity. Okay, so that's when we start out at some velocity, but then we speed up to we speed up steadily or slow down steadily to to a greater speed or a lesser speed. All right, so in this situation, let me just erase this stuff here. And again, we're talking about straight line motion. Okay, so in this situation, an example might be where we're here in, let's say, a car. Try and draw a car with a couple of wheels, not a very good car, but we're at this location. And we're at a traffic light, and now we hit the gas. And in the first second, we travel a certain distance. After 1 second. So this will be, let's say, position 0. After 2 seconds, now we keep getting faster and faster and faster. So in the second second, because we're going faster, we cover a greater amount of distance. So we cover more distance in the second second because we were going faster. And let's say we look at where the car is at the third second, and now the car might be over here at the third second because it's going faster. Now let's say, actually let's say the car was already moving when we first started observing it. So let's say the car was going at 2 meters per second when we first started observing it. And then a second later, it had sped up to 3 meters per second. and a second later it had sped up to 4 meters per second, and a second later it had sped up to 5 meters per second. And so each second it covers more and more distance because it's going faster. All right, well, in this case, what would we say? Our velocity versus time graph might look something like this. It started at 2 meters per second, and a second later, 1 second later, it was at 3 meters per second, and 1 second later, it was at 4 meters per second, and 1 second later, it was at 5 meters per second. And so this graph will be linear. If we have a steadily increasing or steadily decreasing speed, the velocity graph will be linear and non-horizontal. It won't be a flat line, it'll be a sloped line. So it'll either be sloped up if we're increasing speed or sloped down if we're decreasing speed, or if we're increasing speed in the negative direction. But let's just stick with this. In this case, we're increasing our speed in a linear fashion. So one thing we noticed was that the distance that we travel each second gets bigger and bigger and bigger. So our displacement versus time graph is not going to be linear, because each second, the first second, our distance, let's say, increased a little bit up to here, but then our second, we increased a little bit more, and our third second, we increased a little bit more, and after another second, we're going up a little bit more. So we travel, in the first moment in time, we only travel a little bit, our distance only goes up a little bit, our displacement goes up a little bit. The next second, because we're going faster, our displacement goes up more, and the next second, our displacement goes up more. And so when we look at displacement versus time, it is a nonlinear curve. Okay, so displacement versus time will be nonlinear. All right, and how will acceleration look when we have a steadily changing velocity? Well, if we have a steadily changing velocity, in this case, our velocity went 2 meters per second to 3 meters per second. So we increased our change in velocity from during this second was 1 additional meter per second of velocity. And then we went from 3 meters per second to 4 meters per second. So our change in velocity was 1 meter per second of additional velocity. And when we went from 4 meters per second to 5 meters per second, our change in velocity was 1 additional meter plus 1 meter per second of velocity. Okay? So our acceleration is consistent. How much is our velocity changing each second? Well, it changed by 1 meter per second, it changed by 1 meter per second, it changed by 1 meter per second. So we would say our acceleration the whole time was steady. Our acceleration was 1 meter per second of speed change per second, okay, the whole time. You know, at the beginning, after 1 second, at 2 seconds, at 3 seconds, at 4 seconds, we had a steady speed change the whole time. Okay, so this is going to be horizontal, indicating steady, but not zero. Not zero, okay? So if you see an acceleration versus time graph and you see a non-zero horizontal line, that means the object is accelerating. Okay, so again, we're still talking about two situations. We're talking about constant velocity and steadily changing velocity. Those are still the only two situations we're dealing with. We're just looking at different ways of charting what is going on. Okay, so we've been charting a lot of the velocity versus time, but we can also look at location versus time or displacement versus time, and we can look at acceleration versus time as well. All right. All right, now this is basically showing you all possible situations. So looks like a lot at the moment, but let me explain it and hopefully, and I just want to make one overarching point at the end. Okay, so let's talk first about the velocity. So everything up here on top is constant velocity. Okay, constant velocity. So this, and this are all constant velocity situations. So what we have here is a constant positive velocity, okay? Constant speed, and if it's a constant positive velocity, it means you're moving in the positive direction. So basically, we're cruising along in the positive direction. We're moving to the right on a straight line to the right. Okay? So if we're moving at a constant velocity, we're going to have some positive constant velocity. That's just an indication that we're moving to the right. We're moving in a positive direction. So let's say this was positive 3 meters per second of constant velocity. That just means we're covering 3 meters of distance every second, moving in the positive direction. What's our acceleration going to be? Well, we're not changing speed at all, so our acceleration is going to be 0. And what's going to happen to our position? Well, in this case, we're assuming we start at some 0 location, but we're steadily be covering more distance, maybe 3 meters every single second. So our position versus time graph could look something like that. If we started at a different starting position, let's say we started here at 6 meters, and we're moving at a constant positive velocity. Well, we would have started here. We'd record this as our location at time 0, and then we'd cover, let's say 3 meters per second. Then we'd be at 9 meters 1 second later, and 12 meters, and so forth. In this case, our position versus time graph would look like that. So the starting position can affect where your position versus time graph begins, but it's still going to have that positive slope. Okay, if I started off at a negative location, I could start off at negative 3 meters, and if I'm moving at 3 meters per second to the right, I would be here at time 0, and then I'd be here at time 1 second, and I'd be here at time 2 seconds, and I'd be here at time 3 seconds. Okay, so my graph would look something like same slope, but it would be starting at negative 3 meters. So if you see a positive sloped line on the position versus time graph, you know you're moving in the positive direction. Even if you start out at a negative location, you're moving in the positive direction. It means you're traveling with a constant positive velocity. Whenever you see a positive slope on position versus time, it means you're moving at a constant positive speed. Now, what's the alternative? Well, I could be moving in the negative direction. Okay, so if you're moving in the negative direction, how do you think these graphs are going to change? Okay, if I'm moving in the negative direction, well, it simply means I've got a negative velocity. That's our way of indicating direction, the sign, positive, negative. So let's say I was moving at a constant velocity of negative 2 meters per second. Well, what's that going to look like on our velocity versus time graph? It's going to be a steady horizontal line at negative 2 for velocity versus time. And in this case, it's suggesting that we started at some positive position. Whenever you look at these graphs, you want to think of the intersection of the axes as 0 for time and 0 for position, if it's a position versus time graph. And so we would think of this as some positive starting position, maybe over here. This would possibly be considered to be 0 location. So we started at some positive position, and we're traveling at negative 2 meters every second. So each second, we move in the negative direction an additional 2 meters. Okay, so we'd go negative 2 meters, negative 2 meters, negative 2 meters, negative 2 meters, and eventually we would get down to 0. And if we kept going, then our position would simply become negative. Okay, but what this graph suggests is we started at some positive location and we moved in the negative direction at a consistent rate. That's why we have this linear slope to position versus time whenever we have a constant velocity. And again, when our velocity is constant, how much is our velocity changing? It's changing by 0, so our acceleration is 0. Okay, last situation involving constant velocity. So we had constant velocity, we were moving to the right, constant velocity, we were moving to the left, and our last situation for constant velocity is when we're standing still. Okay, so let's say here's our 0 location, and here we're in some positive position, let's say positive 2 meters, okay, and our car is just sitting here. Okay, well, what's our velocity? Well, if the car is just sitting there, our velocity is 0. So this would be velocity versus time. So our velocity is just 0. Okay, well, if our velocity is 0, how much is our velocity changing each second? Well, it's 0 right now. It's 0 a second later. My velocity is 0 a second later. My velocity is still 0 a second later. So my velocity is not changing. And if my velocity is not changing, my acceleration is 0. Okay, so it is possible to have an acceleration of 0 and a velocity of 0. It simply means you're standing still. And in this case, we're standing in some positive location. We're standing at positive 2 meters. So it might be graphed like this, just hanging out, standing still at positive 2 meters. Alternatively, let's say we were standing in some negative, or hanging out in some negative position. Let's say our car is over here, just doing nothing at location negative 1 meter. Well, we graph that like this. My displacement is constant at this location, negative 1 meter. My velocity is 0. My acceleration is 0. Okay, so just want to throw all that out there. It may seem like a lot, but it's all the same thing. It's all constant velocity. It's just constant positive velocity, constant negative speed, or constant 0 speed. Okay? Now, what's the alternative? Well, we said the alternative is we have a changing speed, whether increasing or decreasing. So let's just describe the things you might see. So gaining speed in a positive direction. Well, so I start off and I pick up speed, I increase speed, I get steadily faster and faster and faster. So we would see, as we said, that linear change in our velocity. And if our speed's going up consistently, every second our speed's going up by, let's say, 2 meters per second. So I started out at 0 meters per second, then I was going faster to 2 meters per second, to 4 meters per second, to 6 meters per second, to 8 meters per second. I kept getting faster. Well, what would my acceleration be in that case? My acceleration would be plus 2 meters per second of speed change each second. Okay, but it would be steady, so we should see that non-zero acceleration. Steady acceleration, but non-zero acceleration. And if we're getting faster, we already said, hey, our position is going to change kind of a certain amount at the beginning, but that amount of distance that we cover is going to increase as we go along because we're getting faster and faster and faster. Okay? What if we were doing the same thing but in a negative direction? So we're speeding up, but this time in a negative direction. Well, it's pretty much the same thing. It's just with negative numbers. Okay, so our velocity would, let's say our velocity starts out, let's say we're at a traffic light, and we now are going to accelerate in the negative direction. Well, our velocity would be 0, and our velocity would be getting steadily higher and higher in the negative direction. Okay, and if our velocity, if we're going 0 meters per second to, let's say, negative 2 meters per second, negative 4 meters per second, negative 6 meters per second, let's say our velocity changes by negative 2 meters per second each second. Well, how would we graph that? We'd simply indicate our acceleration, and our acceleration in this case would be negative 2 meters per second each second. And so what's going to happen to our distance? Now, in this case, we're just assuming we started at some positive location. So let's say we have some location over here, 0 meters, and we started at some positive location, let's say plus, I don't know, plus 20 meters, let's just say. And as we start moving, we're covering a relatively small amount of distance in the beginning, but then we cover more distance each second. So maybe the first second we cover a certain amount of distance, the second we cover a greater distance, the third second we cover a greater distance, and so forth. So we would move a little bit closer to position 0 in the first second. In the second we would move more distance toward position 0, and in the third second we would cover more distance toward position 0. Okay, so we're going to get that non-linear shape. Okay, and two last possible scenarios, we're slowing down while traveling in a positive direction. Okay, so in this case, we're say we're driving along the road, and we we pass some position, but so we're driving along, and then we start to slow down. So we cover a lot of distance in the beginning because we're going fast. Then we cover less distance in the next second because we're going slower. Then we cover less distance in the next second because we're going slower. And then we're covering less distance again because we're going slower still. So position versus time, we would have covered a lot of distance in the first second. The second, we would have covered a little bit less distance. The third second, less distance. And the 1 second later, we would have covered, again, we would have increased our distance by a smaller amount each second. So we would have that non-linear curve to it. Non-linear for our distance versus time. Now, speed, on the other hand, we started off at some speed, let's say 10 meters per second. And then we went to a second later, we were at 8 meters per second. And a second later, we were at 6 meters per second. And a second later, we were at 4 meters per second because we're hitting the brakes and we're slowing down the whole time. So our velocity, which started at some positive amount, let's say 10, is decreasing. 10 down to 8. A second later, we're at 6. A second later, we're at 4. A second later, we're at 2. We're decreasing in a linear fashion. Oops, not very clear, but linear. And what's our acceleration? Well, our speed change, 10 to 8, our change in speed would be -2. And here, our change in speed would be -2. And here, our change in speed would be -2 meters per second. So our acceleration would be constant at -2. So you'd see a constant acceleration. All right. And last but not least, losing speed in the negative direction. So same thing, but backwards. So we're going fast in the negative direction, and we slow down. So we're cruising along at a high speed in this direction, but we begin to hit the brakes. We hit the brakes, so we're traveling at some high speed at maybe 10 meters per second, and then we hit the brakes. So second, over here we're at maybe 10 meters per second. A second later, we're at 8 meters per second. But we covered a lot of distance because we were kind of going fast during that time. A second later, we're maybe at 6 meters per second, but we covered less distance because we're going a little bit slower. And then we covered, a second later, we're at 4 meters per second. And again, we covered less distance because we're traveling slower here. And then we keep slowing down uniformly, 2 meters per second. And then we eventually get to stopped, 0 meters per second. Okay, so that would be losing speed in the negative direction. That would be acceleration because our speed is changing, but slowing it, deceleration, okay, and moving in the negative direction. So in this case, we started out at some positive position, and we gradually slowed. So in the beginning, we covered a lot of distance. Then next second, we covered less distance, less distance, less distance. So we get that non-linear curve. Our velocity started out, it should all be negative velocities because we're moving in the negative direction. So our velocity started out at -10, so a relatively large negative value. And then the velocity gradually decreased or steadily decreased down to 0. Okay, so this is again linear and not horizontal. And what's our acceleration? Well, in this case, our acceleration, we were at -10 and we went to -8. So how did our speed change? Well, we consider this a speed change of +2 meters per second because -10 plus 2 would take us to -8. -8 plus 2 would take us to -6. -6 plus 2 meters per second would take us to -4. -4 plus 2 would take us to -2, and so forth. So in this case, we would say we had a positive acceleration of +2 meters per second. Even though we were traveling in the negative direction, our acceleration is positive because we're slowing. Okay, so now let's summarize. So you saw all those scenarios, but there, again, it's really just two situations. The first situation is where we're traveling at a constant speed, whether it's a constant speed in the positive direction or negative direction. So this is our constant velocity situation. Or we have a steadily changing speed, and let's call that acceleration. Okay, so these are our two situations, our constant speed and our steadily changing speed, or our accelerating speed. And what's common? Okay, in all these, let's just go graph by graph. In all of these constant velocity, if the velocity is constant, acceleration is always zero. Okay, so when we're at constant velocity, the acceleration versus time graph is always going to show zero. If you see zero acceleration, you know we're moving at constant velocity. If I showed you a graph of acceleration versus time and it's zero, you should say you're not accelerating, that's constant velocity. Then constant velocity might be constant velocity in the positive direction, it might be constant velocity in the negative direction, or it might be constant velocity of zero, meaning standing still. But if I see acceleration steady at zero, it means we're moving at a constant velocity. Okay. Now your velocity is going to be a horizontal line. Okay, so your velocity is a horizontal line. Okay, in all cases, right? It's a horizontal positive line to represent constant positive velocity. It's a horizontal line below the axis, indicating a negative constant velocity, or it is a horizontal line at zero, indicating constant zero velocity. Okay, and our position, because we're moving at the same speed, our position is linear. Okay, so our position or displacement graph is going to be linear, straight line. Okay, straight line going up if we're moving in the positive direction there, straight line going down if we're moving in the negative direction, and straight line horizontally indicating standing still. Now let's compare that to our second situation, which is when our speed is steadily changing. Okay, well, when our speed is steadily changing, it's either steadily going up or steadily going down. Okay, so it's our speed is either steadily going up in the positive direction, steadily going up in the positive direction, or steadily going down. Okay, if we're moving in the negative direction. Steadily going up or steadily going down. That doesn't really say anything about direction, but if it's above the x-axis, it means we're above the this axis. It means we're moving in the positive direction, but steadily changing. Here we're above the x-axis, so we're still moving in the positive direction, but steadily changing, steadily slowing. Okay, so our velocity versus time graph, well, since our speed is steadily changing, is going to be linear, and not horizontal. Because if it was horizontal, if it was like this, this is technically linear because it's a straight line. If it was horizontal, it means we're moving at a constant speed. So it's either got to be sloped upward or sloped downward. So straight line, sloped upward or sloped downward means we are changing speed, means we are accelerating. Okay, if we're changing speed, we're either consistently changing speed. We either have a consistent positive speed change or a consistent negative speed change. So what are we going to get for acceleration versus time? We're not going to get zero. We are going to get a horizontal line, but it's going to be non-zero. So what you'd look for here is a horizontal line, but not at zero. Okay. So if we have a positive acceleration or a negative acceleration, it means our speed is changing in a positive way or a negative way. Okay, so a horizontal line above or below the x-axis is an indication of acceleration, of linear speed change. Okay, and as we said, whenever our speed is increasing or decreasing in a consistent way, we're going to get this non-linear shape to displacement. So if you see non-linear in displacement versus time, you know we have a situation of acceleration. Okay? This is nonlinear, 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 nonlinear. Okay, so let's compare these things that we just said. All right, constant velocity, you're going to see zero acceleration, a horizontal steady velocity, and a linear change in displacement. If our speed is steadily changing, if we're accelerating, we're going to see a non-zero, a steady horizontal line representing non-zero acceleration. So a steady horizontal line, but not at zero. So a steady horizontal line above or below the x-axis indicating steady or consistent speed change. We're going to see a linear change to our speed versus time because our speed is going to be steadily going up or steadily going down. And we're going to see a non-linear position versus time graph. All right, so you got to get these, this is it right here. If you get this relationship down, that when you're accelerating, you're going to see these shapes. When you're at constant velocity, you're going to see these shapes. Then you'll get all these questions right. All right, let's go to the next page. So now we're going to use what we just learned to solve some problems. Well, the first thing you need to do is look at the axes. So this question is saying, which pair of graphs represents the same motion? Okay, the same motion. Now what they mean by that is you can either have constant velocity or you can have steadily changing velocity or acceleration. Okay, so it means which two graphs both show constant velocity or which two graphs both show steadily changing speed or acceleration. All right, so let's start here. Number 3. Okay, so we can see the velocity is linearly changing. That is an indication of acceleration. Here we see displacement is linearly changing. That is an indication of constant velocity. Therefore, these are definitely not the same motion, and we can eliminate this. Okay. Here, let's go to question 4, or answer 4. Here we see a steady velocity. Okay, this is an indication of constant velocity. But here we see non-linear curve under displacement. This would be an indication of acceleration. So these are not the same motion. Okay, here we see a constant velocity. This is a constant velocity. And here we see linear displacement versus time, which would also be an indication of constant velocity. But this is a negative constant velocity. Think of it as like -3 meters per second. That means you're moving steadily in the negative direction. If you're moving steadily in the negative direction, you should not be, your location should not be getting more and more positive, right? This is like, think of this as I'm located at -10 meters, and later on I'm located at +10 meters. Okay, this positive slope means you're moving in the positive direction. You've got a positive velocity. Okay, so that's the problem with this answer. They both are graphs that are consistent with constant velocity, but this is constant velocity in the negative direction, and this one is indicating constant velocity in the positive direction. Okay, so we eliminate that. This one indicates a steadily increasing velocity, so this is definitely acceleration, getting faster and faster and faster. And when you're accelerating, we expect to see that nonlinear displacement graph. Okay, and we have a positive velocity. We're moving in we have ever greater and greater positive displacement. So this is also an indication of acceleration, and this would be our answer. Okay, let's do one more. Which graph represents the motion of a block accelerating down an inclined plane? So just something that's, an inclined plane is just a ramp. Okay, so this block is sliding down this ramp, and it's getting faster and faster as it goes down the ramp. So it's accelerating. All right. Well, we know if an object is accelerating. Now let's look at our axes. This is distance. This is displacement. This is position. Okay, so distance. This is not velocity. This is not acceleration. This is distance. This is also distance, distance, distance. And this is time, 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 time. Okay, so they're all distance versus time. So what do we know about distance versus time when we're accelerating? We know it should be nonlinear. Okay, so this would be, this distance obviously is linear, and it is rock solid steady. This would be an indication of standing still. Our position is not changing. So this is clearly not accelerating. This is standing still. This is a constant velocity of 0. Okay, if my location or displacement is steadily, or distance from, let's say, the origin, again, we're traveling along a straight line. Let's say this is 0. If my distance is getting steadily, is going linearly up, this is an indication of constant velocity. My position changes by the same amount each second. I go up by 5 meters. A second later, I'm at 10 meters. A second later, I'm at 15 meters. A second later, I'm at 20 meters. Right? This is a linear change in distance with time, which is an indication of constant velocity. Okay, so we know this is, and this one we said was constant velocity as well, constant velocity of 0. Okay, so this is constant velocity, so that's not accelerating. Okay, and this, when I have a linear slope, this is constant velocity during this period of time, and then it looks like the object stopped and became a constant velocity of 0. So this is definitely not accelerating. And this, here we have our nonlinear shape, which we know for distance, linear, and that's what we want to see when we're talking about distance versus time and acceleration. So we would say, yep, that's our answer. Okay, so I'm going to send you a couple of things to read along with this, but I'm hoping you got the idea that you can answer these kinds of questions just by knowing this, that if it's a constant velocity situation, you're going to have rock solid 0 acceleration. You're going to have a horizontal line for velocity, and you're going to have a linear line with slope for, or a linear line for position. If we're accelerating, you're going to have a horizontal line for acceleration, but it's not going to be at 0. So it's going to be a horizontal line above or below the axis, depending on whether you have positive or negative acceleration. You're going to have a linear change in your speed or velocity, and you're going to have a non-linear change in your distance or displacement. And then once you get that, once you see how these all represent constant velocity and these all represent steadily increasing speed, then you can answer these questions without too much difficulty. All righty. Thank you.